All right, this is part 2 of the section 4.3 study guide. I think it cut off on number 20, so I'm going to go ahead and start with number 20 again. I didn't know that it cut off, so I just kept talking and talking. So this is my second or third time to walk through this, and doggone it, it only records up to 20 minutes at a time. So let's get going so we can get this one done. So number 20, it says, what isotope of carbon has been chosen as the reference isotope for atomic mass units? Well, what we do is we are using carbon-12, okay? Carbon-12 is our chosen isotope for all of the AMU system. And how many AMUs does carbon-12 have? Well, it has 12 AMUs. So that is our standard for reference or comparison. For all the other elements, we use carbon-12. And it's a good one to use. I mean, it's relatively abundant, it's easy to identify, easy to mass, and those kinds of things. So that's what we use. There it is, long story short. We could get into the details of it, but let's just move on, shall we? So number 21, is the following sentence true or false? The atomic mass of an element is always a whole number of atomic mass units. The answer to that is a big time false, okay? No, atomic mass is actually going to be a compilation of all the masses, so I'll say of masses and percents, percent abundance of all isotopes. And I don't know about you, but that's not going to be a whole number anything. That's going to be percents and decimals and all kinds of things. And in fact, we're going to be calculating one of those here in just a minute. So in this situation, the answer is absolutely false, okay? So number 20, circle the letter of each statement that is true about the atomic mass or average atomic mass of an element and the relative abundance of its isotopes. So let's look at letter A. In nature, most elements occur as a mixture of two or more isotopes. That is so true. Okay, so this one is true. Absolutely. It says circle the letter, but I just circled the whole thing. The next one, isotopes of an element do not have a specific natural percent abundance. That is, let's see, let's just do this. We'll make that one black. And I'm going to say, no, that's false. And then the next one, the average atomic mass of an element is usually closest to that of the isotope with the highest natural abundance. That, my children, is absolutely true. Whoops, I picked red instead of orange, didn't I? That one is true. And then the last one, because hydrogen has 3 isotopes with atomic masses of at 1 AMU, 2 AMU, and 3 AMU respectively, the average atomic mass of natural hydrogen is 2 AMU. Nope, that is not true. The average atomic mass of hydrogen is actually 1 AMU. How can it be that if there's some that are 2 and some that are 3? Well, the 2s and 3s are very, very rare, okay? They are very rare. And because they're so rare, the other one is so abundant that these guys down here don't even hardly count towards the total AMU of hydrogen. All right, the next one, circle the letter of the correct answer. When chlorine occurs in nature, there are 3 atoms of chlorine-35 for every 1 atom of chlorine-37. So we have the 3-to-1 ratio, 35 to 37s, okay? Which atomic mass number is closer to the average atomic mass number? Well, obviously the 35 is, because there's 3 times more of them. Okay, so this one is 3 times more abundant. And because it's 3 times more abundant, then we know that the actual atomic mass is going to be a lot closer to that 35. All right, let's keep cruising along here. Here's the answers to the guided practice problems, where I remember I told you I walked through all these already and actually recorded all of them, but anyway, we'll put them on here. So I can probably clean up some of these things. Instead of looking all messy like that, we'll just write down atomic atomic number, and the atomic number is going to be 6. The mass number right here is going to be 12. And here's how we actually write it. We usually put the mass number on top and the atomic number on the bottom. And on the next one, let's see, except for hydrogen, let me erase this and see what I'm looking at. Except for hydrogen 1, the mass number of an isotope is always greater than its atomic number. And the answer is yes, it really is. And in the case of hydrogen, it's not that case because hydrogen usually doesn't have neutrons. It only has a proton, so it's going to be the same for it. So here we go, fluorine 19, its atomic number is 9, and its mass number is 19. And so, of course, here's the mass, and here's the atomic number. And the mass number is greater than the atomic number, and that's the answer down here at the bottom. And on the next page, beryllium. Beryllium has an atomic number of 4 and a mass number of 9. As you can see here and here, that's how they go. The mass is usually on the top and the atomic number is usually on the bottom. And is this answer reasonable? Yes, because the mass is usually greater than the atomic number. Okay, unless it's hydrogen, the mass is always going to be greater than the atomic number. Now, look at the big idea. It says, how do you determine the number of electrons, protons, and neutrons in one atom? Now, we've talked about this in class, and I've even given you all these rules, right? The atomic number equals the number of protons. That's this rule right here. The next rule, protons equals the electrons in a neutral atom, and that's what we have here. And then finally, the mass minus the atomic number, that's atomic number, that's going to equal the number of neutrons. So when you do that, and when you use this, whoops, about to run out of battery power here next. Oh my goodness, we just got problems everywhere. You're going to end up with these numbers down here at the bottom. And I'm just going to go ahead and leave them in there. I'm not going to erase them. If you had heard me talk about these before, then you would see how I got those numbers. But I'm going to just give you the answers at this point. You're just going to use those 3 rules up above and come up with those answers. So you can hit pause and get those if you want, but I'm going to move on. Let's move on to the next one. Defining the atom. This is basically 4-1 review up here. So that's what we're looking at right now. We're just reviewing. So who came up with this idea that atoms are small indestructible particles? That was Mr. Democritus, okay? And then the next one, who used experimental methods to propose an atomic theory? That would be John Dalton, of course. And then finally, what is the name of the microscope that we use to actually try to look at atoms? We use the scanning electron microscope. Then we went on to section 4.2, and there's some things in here. The particles that make up atoms are known as subatomic particles, and they are housed either in the electron cloud or in the nucleus. Okay, nucleus goes here. And then most of the volume of an atom is the volume, by the way. This is the volume, which means the size, right? Size and volume are the same. That's occupied by the electrons. That's the mostly empty space area. The mass is mostly in the nucleus, and that's made of protons and neutrons, okay? So number 7, the identity of an element is determined by the number of protons, yes. And each of an element's isotopes has a different number of neutrons and a different mass number. And then number 9, the atomic mass of an element is the weighted average of all the isotopes. Yes, this weighted average thing. So now we're going to work one of those problems and then we are done. So look at number 1 up here. It says how many neutrons are in an atom with an atomic number of 53 and a mass number of 127? Well, of course we know the mass number, I'm on this right here, the mass number minus the atomic number is going to equal the number of neutrons. So we have the mass number of 127 minus 53, and we're going to end up with 74 neutrons. Number 2, in a mass or in a sample of silver, how are we going to come up with this? We're going to take 51.84% of the atoms have a mass of this, and 48.16 of the atoms have a mass of this. Well, we're going to take mass number 1, which would be this 106.95, okay, times the relative abundance for that, and the relative abundance is this guy right here, the 51.84, plus mass number 2, which would be this guy right here, there's mass number 2, times the relative abundance of it, which is 48.16. And we're going to put those together down here, 106.905 times 0.5184. Where did I get that? Well, you take the percent and you just get rid of the percent, which means you have to move that decimal over here, right? Plus 108.905 times 0.4816. And you end up with 107.87 AMUs. Here's the explanation for that down here at the bottom. I actually gave it up here, right? So there's that. And then let's see, the next one down, the center of this atom is called the nucleus. The atom contains 5 protons and 5 electrons, yes. The atom also contains 6 neutrons. The atomic number of the atom is 5, yeah. The mass number is 16. And the atomic mass of a sample of an element is 10.81, and this is AMUs, or atomic mass units, okay? And then finally the last word, the one we keep seeing, isotopes, 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 which are variations of elements. Okay, so hopefully that gets you through part 2 of section 4.3 study guide.